In these slides, we want to discuss what capacitors in parallel look like, what the parallel connection looks like, and see how to find one capacitor that does the same job as two capacitors in parallel. So parallel connection means that you take the battery, you go put one capacitor with like this as shown here, and then put other capacitors shown here. So the left plate of this capacitor is connected to the left plate of this capacitor, is connected to the left side of the battery, and the right side of this plate is connected to the right side of this capacitor, and it's connected to the right side of the battery. So this is what a parallel connection looks like. So when the battery supplies charge to the capacitors, this capacitor will have charge plus Q1 on the left, minus Q1 on the right. This one will have plus Q2 on the left, minus Q2 on the right. This slide shows the potential at different points in the circuit. So everywhere in red has the same potential. Remember, in the chapter on potential, we showed that a conductor in electrostatic equilibrium, every single point on this conductor or inside the conductor has the same potential. So if you take the left side of the battery and you take this wire and the left plate and this wire and the left plate here, all this is one conductor. So if you find the potential anywhere at any point on the wire or on the plate, it all has the same potential in equilibrium. The same thing for the right side. Any point on this plate or this wire or this plate or this wire or this left side of the battery, all this is at the same potential. There's a potential difference across the battery. There's a potential difference across the capacitor, and there's a potential difference across this capacitor. But if you're on the right side, all the potential is the same. If you're on the left side, the potential is all the same. So let's identify some points here, and we'll see what the relation of the potential is for these points. So this point is on the left side of capacitor 2, and let's call the potential here V plus Q2. So it's the potential on the plus side of the second capacitor. And the potential at this point, we'll call it V plus Q1. And the potential on the left side of the battery, we'll call it V plus. And the potential on the right side of this capacitor, we'll call it V minus Q2. It's the potential of the negative plate. And the potential at this point, we'll call it V minus Q1. And the potential at this point, we'll call it V minus, the right side of the battery. So what's the relationship between all these potentials? So we know, as we just mentioned, all these points have the same value of potential. So the potential here is the same as the potential here is the same as the potential here. And all the points on the right, on the blue side, all of them have the same potential. So if we define then the potential difference across capacitor 2 to be the potential here minus the potential here, and we define the potential difference across capacitor 1 to be the potential here minus the potential here, and we define the potential difference of the battery to be the potential here minus the potential here, then what's the relationship then between these potential differences? Clearly the potential differences are all the same, because this is the same as this is the same as this, and this is the same as this is the same as this. So when you take the difference between them, they all give you the same number. So for a parallel connection, the thing that characterizes a parallel connection is that the potential difference across the capacitors is exactly the same, and it's the same as the potential difference across the connected battery. So the question that we want to look at now, we want to replace these two capacitors by one capacitor that does the same job. So before we do that, we need to know how much total charge does the battery provide on each side. So on the left side, how much charge does the battery supply on the left side? It supplies Q1 and Q2. So it supplies a total amount of charge of Q1 plus Q2. So we want to do what? We want to replace those two capacitors by one capacitor called the equivalent capacitor that does the same job. Does the same job meaning that for the same potential difference, it supplies the same amount of charge on each side. So the charge Q on this left plate should be Q1 plus Q2. And of course, if you use the equation for the capacitance for the equivalent capacitor, the charge Q is equal to C equivalent delta V. We have now the original circuit and the equivalent circuit. So we want to replace these two capacitors by this one. And we said that this charge Q has to be the sum of the charges Q1 plus Q2. So we know that Q is C equivalent delta V, and we know for capacitor 1, Q1 is C1 delta V1, and we know for capacitor 2, Q2 is C2 delta V2. These are the relations for each capacitor, the C1, C2, and C equivalent. So we can take Q here and replace it by C equivalent delta V. We can take Q1 here and replace it by C1 delta V1, and we can take Q2 here and replace it by C2 delta V2. And then now the question, what is delta V and delta V1 and delta V2? How are those related to each other? We just proved before in the beginning that the potential difference is exactly the same because the connection is in parallel, and that the thing that characterizes the connection in parallel is that the potential difference across C1 is the same as the potential difference across C2. It's the same as the potential difference of the battery. All these can cancel, and you get the simple result that the equivalent capacitance is the sum of the two capacitances that you have in the problem. So the thing that characterizes a parallel connection is that the potential difference across them is all the same, and that the equivalent capacitance is equal to C1 plus C2.